find the number of proton NMR signals for these compounds. Okay. Yeah, for the first compound, it is orthodichlorobenzene or 1,2 dichlorobenzene. This is actually a symmetrical molecule. Okay. So this proton and this proton, okay, they are actually equivalent. Okay. So this proton and this proton, they are equivalent. This is proton A, this is also proton A. So these two protons will give one signal, and this proton and this proton, they are equivalent. They will give one signal. So orthodichlorobenzene, okay, will give two signals in the proton NMR spectrum, right? Then in metadichlorobenzene, you can also use the plane of symmetry idea here, or axis of symmetry. Yeah, so if I keep a plane here, suppose if I keep a plane here, then the protons in the left hand side and the protons in the right hand side, they are equivalent. So here I have two protons, therefore we will get two signals. Okay, two different protons. Similarly here, see, here also in this compound, this protons, here we have one proton. This is in one environment because they are close to the two chlorine atoms. Okay, they are between two chlorine atoms, this proton is there. So this proton is in one environment, and these two protons, this proton is adjacent to this chlorine and this proton is adjacent to this chlorine. Okay, something like ortho, right? So these protons are in one environment, and the proton which is present here is in a different environment. So metadichlorobenzene has three different types of protons, so we get three signals in the proton NMR spectrum. Whereas in the case of paradichlorobenzene, right, see, this proton is like ortho with respect to this chlorine, and this proton is also ortho like this chlorine. So I can say that these two protons are equivalent. Similarly, these two protons, which are also ortho-like from this chlorine, therefore, all the four protons are in same environment. Okay, see what I am trying to say. Suppose if you take this proton, for this proton, this is ortho. This chlorine is in ortho position, and this chlorine is in meta. So one chlorine is ortho, another chlorine is meta. Similarly, you take any one. See this proton, this is ortho, and this proton is meta. This chloro is meta from this, right? So all the chlorines, all the hydrogens are in same environment. Therefore, all the hydrogen atoms are equivalent. So this will give one signal in the proton NMR spectrum, paradichlorobenzene. Now I have two different substituents. One is chlorine, the other one is bromine. So this is called, this is position 1, this is position 2. It is called 2-chlorobromobenzene. In 2-chlorobromobenzene, how many signals we get? Here listen, this hydrogen, it is close to this bromine, but it is far away from this chlorine. So this hydrogen is different. Let me take HA. And what about this hydrogen? Listen, this hydrogen is close to chlorine, but away from bromine. It is like meta from bromine. So this hydrogen is different. These two hydrogens not in same environment. See, this hydrogen is close to bromine, whereas this hydrogen is close to chlorine. They are in different environment, so they will give different signals. Similarly, this hydrogen, okay, let me take this HC. This hydrogen, it is meta to bromine and para to the chlorine. Okay, so this hydrogen is in one environment, whereas the other hydrogen, for this, isn't the chlorine is meta and the bromine is para. So all the four hydrogens are different here, so we get four signals for this compound. Okay, then what about here? Here also, this proton, which is in between chlorine and bromine, which is in one environment, and this proton, HB, which is close to bromine but para to chlorine, and this proton, let me take, see, this is close to chlorine, ortho to chlorine, but para to bromine, and this proton, This is meta to chlorine and meta to bromine, which is in a different environment. So this molecule in which the 4 hydrogen atoms are in different environment, so we get 4 signals in the proton NMR spectrum. Okay, what about here? See, the 2 hydrogen which are ortho to chlorine, they are in one environment, and the 2 hydrogen which are ortho to bromine and para to the meta to the chlorine, they are in one environment. So we get 2 signals, okay, for this compound in the proton NMR spectrum. Right? For cinnamic acid, this hydrogen will give one signal. This hydrogen will give one signal because it is close to carboxylic acid, and this hydrogen will give one signal. Okay, in phenyl ring, see, these 2 hydrogens, ortho hydrogens, are equivalent. So let me take, see, suppose I mention this is A, this is B, this is C, and this is D, this is also D. If this is E, this is also E, then the para hydrogen is different, which is F. Okay, so this compound has 1, 2, 3, 4, 5, 6 different types of protons. So we get 6 signals, okay, in the proton NMR spectrum of this compound. Right? In allene, listen, in allene we have what is called plane of symmetry as well as C2 symmetry. So all the 4 hydrogens are equivalent. Listen, by observation, by just seeing the molecule, we can say that these 2 hydrogens are in one plane, these 2 hydrogens are different plane. So we may think that these 2 are in one environment, these 2 are in different environment. But actually speaking, by means of rotation symmetry, right, we can bring these 2 hydrogen here and we can bring these 2 hydrogen here. So they are equivalent. Okay, or you can use also substitution method. If we substitute, if you replace this hydrogen, I will put chlorine, I'll get one IUPAC's name. If you replace this hydrogen and I will put chlorine, I'll get the same IUPAC's name. So all the 4 hydrogens are equivalent in this case. So we get only one signal in the proton NMR spectrum of allene. Okay. So try to find number of signals for these compounds in the proton NMR spectrum. Yeah. In the case of naphthalene, how many different types of protons we have? See here. So we have proton here. We have proton here. Let me take these 4 protons first. These 4 protons, they are equivalent. Okay. See, I can keep a plane here. I can keep one more plane here. Observe carefully. Now, see, this is a plane, mirror plane. This is another mirror plane. Okay. We have 2 mirror planes like this. And between the 2 mirror planes, how many protons are there? See, I have 2 protons, right? Here one, here one. So this will give one signal and this will give another signal. Similarly, if this is A, HA and this is HB, here this is HA and this is HB. Similarly, here this is HA and this is HB. And this is HA and this is HB. So in naphthalene, we have 2 different types of protons. So we get 2 signals for this compound in the proton NMR spectrum. What about in the case of anthracene? See, in the case of anthracene, observe carefully, here also we have a plane here. We can keep a plane here and we can keep another plane here. There are 2 planes of symmetry possible. And one more plane which is passing through all the atom, which is not important for us. So I am going to consider these 2 planes. Between the 2 planes, how many hydrogens are there? See, here I have 1 hydrogen, 1. Here I have 1, 2. And this plane has 1 hydrogen, so 3. Okay. So HA, HP, and this is HC. So I have 3 different types of protons. Similarly, here I have 3, and these 3 and these 3 are equivalent. And here I have 3, this 3 and this 3 are equivalent. So we have 3 different types of protons in this molecule. So this molecule will give 3 signals in the proton NMR spectrum of the compound. Okay, take it. Yeah, this is naphthalene, this is anthracene, and this is phenanthrene. In phenanthrene, we have a plane. Okay, so we can keep a plane here, plane passing through the center of this benzene ring. Okay, if you do reflection, you will get equivalent shape. Now listen, how many protons are there? See, I have 1 proton here, H. See, let me take this HA, and here no proton. Here I have one proton HB, here I have one proton HC, here I have one proton HD, and here I have another proton HE. Okay, so I have 5 protons this side. Similarly, these 5 protons are equivalent. So phenanthrene has 5 different protons, therefore it gives 5 signals in the proton NMR spectrum. Okay, take note. This compound is called chromone. And here there is no symmetry element present, no plane of symmetry, no axis of symmetry, right? Therefore, all the hydrogens are in different environment. That's the meaning. So here I have one hydrogen, HE. Here I have one hydrogen, HB, HC. Listen, though they are benzene ring, but this side, see, this hydrogen, it is connected to this carbon. This carbon is close to this oxygen, ether oxygen. Whereas this hydrogen, which is connected to this carbon, which is close to the carbonyl group. So these 2 hydrogens are not in same environment. So this is HC and that should be different, HD. And this is HE and this is HF. So this molecule has 1, 2, 3, 4, 5, 6 different types of protons. So it gives 6 signals in the proton NMR spectrum. Now let me move on to the pyridine. In pyridine we have a plane of symmetry. See here, we can keep a plane passing through this carbon and the nitrogen. You can separate this into 2 halves, and we have 2 protons here, 1 proton here and 1 proton here, HB, and 1 proton passing through the plane. We should count that also. So this molecule has 3 different types of protons, so we get 3 signals in the proton NMR spectrum. Okay, for pyridine. Then what about pyrrole? In pyrrole, yes, this hydrogen will give one signal, HEA. Let me take this HEA. And these 2 hydrogens are equivalent. HB, you can take plane also. Okay. And here, this hydrogen HC and this hydrogen also HC. So we get 3 signals for this compound called pyrrole. Pyridine will give 3 signals. Pyrrole also will give 3 signals in the proton NMR spectrum. And this is indole. In indole, there is no symmetry element present, so all protons are different. So we have, see, 1 proton HA, this is different, HB, HC, HD, HE, HF, and this is HG. So how many different protons are there? 3, 4, 5, 6, 7. So we get 7 signals in the proton NMR spectrum for this compound. And this is quinoline. Yes, quinoline also. In quinoline, there is no symmetry element. So all the protons are different. How many protons are there? 1, HA, HB, all are in different environment. HC, HD, HE, HF, and HG. So we have 7 different types of proton. So we get 7 signals. This is quinoline. And what about this? This is isoquinoline, right? Quinoline and this isoquinoline. In isoquinoline also there is no symmetry element present. Okay. There is no symmetry element perpendicular to the molecule. There is no plane perpendicular to the molecule. Okay. Therefore, it is highly unsymmetrical molecule. So all the hydrogens are non-equivalent. So we have, see here, one hydrogen HA, HB, HC, HD, HE, HF, and HG. Yes, all the protons are in different environment. So this compound will give 7 signals in the proton NMR spectrum. Okay, then this question is appeared in 2015 December CSIR JRF net examination. How many signals we get for this compound? Okay, in proton NMR spectrum. Okay, let me do it here. So this compound, let me draw. 6. One second. Committing mistake. Yeah. And we have methyl groups attached here. Yeah. This is the compound given. I have drawn in a form like this. So we have 26 carbon atom. So let me take this is carbon 1. Between carbon 1 and carbon 2 we have double bond. So let me put a double bond here, and we have a methyl group here. Okay, methyl group. So 1, 2. This is carbon number 3, and this is 4, 5, and this is carbon number 6. Okay, yeah. So I have drawn this compound. In this manner. They are actually one and the same. Now, how many different types of protons we have? See, here I have methyl group, and all the hydrogens are in same environment, so we'll get one signal for that. Then here I have an hydrogen. That hydrogen will give one signal. So it will show like this, Hb. And here we have two hydrogens. Right? They'll give one signal, and okay, first I'll write the hydrogens. So this is 1, 2. Here we have 2 hydrogen, and here we have 1 hydrogen. Here we have 1 hydrogen. Here we have 2 hydrogens. Okay, and here we have 2 methyl groups. Yeah. See, this hydrogen and this hydrogen, they are not equivalent, because this is something like exo-endo like hydrogen. So this is something like exo, and this is something like endo. So they are in a different environment. Okay. So if this is A, this is B, then this will give one signal, C, D, E, F. Okay, then these two methyl group, G, H. Okay, why these two are different? Because I have a double bond here. This methyl group is towards the double bond, and this methyl group is away from the double bond, so they are in the different environment. Okay, due to anisotropic effect, this methyl and this methyl, okay, appear in a different chemical shift value. Okay, so how many protons we have? So 1, 2, 3, 4, 5, 6, 7, 8, and here 9 and 10. E, F, G, H. This is I, and this is J. We get 10. Why these two are different? Because if I replace one hydrogen by another, this will give diastereomers. Okay, here I have cis trans isomer, and this carbon, if I replace one hydrogen by a different group, yes, these two hydrogens are enhanced. These two hydrogens are diastereotopic hydrogen, so they'll give different signals. So this compound will show totally 10 signals in the NMR spectrum. Okay, 10. Now the next one is that how many signals we get for these two compounds, for this compound. Okay, yeah, listen, this is actually a symmetrical molecule. So the protons attached to this methyl group and the protons attached to this methyl group, they are one and the same, they are equivalent. See, if you fix an axis passing through this middle carbon and the center of the molecule, if you fix an axis like this, and if you rotate by 180 degree, I'll get equivalent structure. Therefore, this proton and this proton, they are equivalent. The protons attached to this methyl group and the protons attached to this methyl group, they are equivalent. And this proton, I'll say Hb, and this proton is also Hb. They are equivalent. And here I have one proton Hc, and this is Hc. They are equivalent. Okay. Now, listen carefully. This is an asymmetric carbon. Why? For this carbon, see, this side I have a double bond with the methyl group is attached first, and this side I have double bond where the methyl group is attached to the next carbon here. Okay, and above we have CH2 group. Therefore, all the 4 groups are different. Therefore, this carbon is asymmetric already. And the hydrogen, 2 hydrogen present on this carbon, okay, they are actually diastereotopic hydrogen. If I replace 1 hydrogen, I'll get 1 isomer. If I replace this hydrogen, I'll get another different isomer. So it's a diastereotopic hydrogen. So this will give one signal and this will give one signal in the NMR spectrum. So how many signals we get? See, A, 1, B, C, 3, 4, 5. So this compound will give 5 signals in the proton NMR spectrum. Okay, take 2. So, listen. Suppose if we have a signal, the signal gets split. The signal gets split into 2 or 3 or 4. It depends upon the non-equivalent protons, right? Depends on non-equivalent protons present. Okay, how many non-equivalent protons present, right? Listen, after splitting, we get the signal is split into number of lines, also called peaks. Okay, so a signal after splitting, right, because of splitting by the neighboring protons, what will happen? We get what is called peaks, also called lines. Okay, so a signal split into peaks, right, depending upon the neighboring hydrogens, the number of neighboring hydrogen present, and the hydrogen should be non-equivalent. Okay, now listen, how many peaks we'll get? Okay, it depends on number of neighboring hydrogen, I have told you. Okay, and to find the number of peaks and to find the intensities of those peaks, okay, we have what is called the Pascal triangle method. Okay, I'll just introduce you what is Pascal triangle. Using that, how to find the intensities of the peaks that we obtain. Okay, now listen. So, number of peaks obtained by splitting. This is the general formula. 2 into how many nuclei are there, then what is the I value of those nuclei plus 1. This is the formula we use to find the number of peaks, okay, obtained by splitting using the non-equivalent protons present in the adjacent carbon or in some position. Okay, listen carefully. In the case of suppose I have a proton Ha, right? This proton signal, it will give some signal. This signal is split into doublet or triplet or quartet, depending upon number of hydrogen present on the adjacent carbon. Suppose if I have hydrogen carbon, say Hb, adjacent carbon, I may have 1 Hb, I may have 2 Hb, I may have 3. It depends on the molecule. Okay, and what is the I value for the proton? I value for the proton is half. Okay, if I is equal to half, how many peaks we get? Okay, see, I have a proton A. That proton A will give one signal in the NMR spectrum. This signal is split into doublet or triplet or quartet or quintet, depending upon number of hydrogens present on the adjacent position. Okay, now since those adjacent hydrogens for which the I value is equal to half, okay, we can predict the number of signals, peaks. We can predict the number of peaks. We can also predict the intensities of those peaks using Pascal triangle. Okay, so let me introduce what is Pascal triangle. Listen carefully before it goes into that. Listen, first I'll write this. For I is equal to half nuclei. Okay, if any nucleus has I is equal to half, then number of peaks or lines number of peaks, also called number of lines. Okay, number of peaks or number of lines obtained by the splitting of one signal, okay, is equal to 2 into n into I value is half, I'll put half here, plus 1. So this 2 cancel, we get what is called n plus 1 peaks. Okay, so for a proton, in the case of proton NMR, if I have one signal and that signal is split into doublet or triplet or quartet or quintet depending upon the number of adjacent protons present, and since adjacent protons also have I equal to half value, okay, we get what is called n plus 1 peaks, okay, for each signal, right? So what I am trying to say, we'll discuss everything, right? Now listen, if I is equal to half, right, to find the peak intensity, we get peaks. To find the peak intensity, we can use what is called the Pascal triangle, right? So what is Pascal triangle? We'll discuss. Pascal triangle. Okay. Now, first we'll start with the, say, n is equal to 1, right? Suppose if n is equal to 1, then the signal is split into a doublet. The signal is split into a doublet, right? Let me start from n is equal to 0 so that it is easy. Suppose if n is equal to 0, meaning there is no neighboring hydrogen. When there is no neighboring hydrogen, then how many signals we get? We get only one signal and the intensity is 1. Okay, I can call this as a singlet. No splitting, so we get singlet and the intensity is given as 1. If n is equal to 1, what is the meaning? The adjacent carbon has one hydrogen. If the adjacent carbon has one hydrogen, then the signal for HA proton is split into a doublet. And what is the intensity? Peak intensity? Very simple. What to do? To this one, add zeros both sides. Observe carefully. Add 1 0 this side and 1 0 this side. Then add two numbers. First add these two numbers. 0 plus 1 is 1. Okay, 0 plus 1 is 1. Similarly, add the next two numbers. 1 plus 0, this is also 1. So, you'll get, if the neighboring carbon has one hydrogen, then the one hydrogen split the signal of HA proton. Okay, what I'm trying to say. I have HA proton and the neighboring carbon has one hydrogen. This hydrogen split the HA proton signal into a doublet. You'll get two peaks. And what is the intensity ratio? Intensity ratio is 1:1. Right? Suppose if I have n is equal to 2, there are two equivalent hydrogens. There are two hydrogens present on adjacent carbon. Okay, suppose if I have one more hydrogen here, then the two hydrogen split the signal of A into a triplet. How? Put n is equal to 2 in this formula. 2 plus 1 is 3. We get triplet. For triplet, what is the intensity ratio? Very simple. Listen, add two zeros both sides. Add 1 0 this side and 1 0 this side. Then add two numbers. Okay, I'll add these two numbers. 0 plus 1, yes, I'll get 1. Then next two numbers, 1 plus 1, 2, 1 plus 0, 1. So, the intensity ratio is 1:2:1. Okay, for triplet, the intensity ratio is 1:2:1. Okay, the next one, if n is equal to 3, suppose adjacent carbon has 3 hydrogen, then the signal for HA proton split into quartet. Okay, if it is split into quartet, what is the intensity ratio? Very simple. Add 1 0 to the left hand side, add 1 0 to the right hand side, then add two numbers. If you add these two numbers, 0 plus 1 is 1. Then add these two numbers, 1 plus 2 is 3, 2 plus 1 is 3, and 1 plus 0 is 1. So we get the intensity ratio as 1:3:3:1. Okay, let me write here so that it is easy for us. So singlet means 1, doublet means 1:1. Okay, triplet means 1:2:1. Quartet means 1:3:3:1. This is the idea. Right? Then to find quintet, what to do? Same idea we should follow. Suppose if n is equal to 4, suppose we have 4 equivalent hydrogen. Okay, 4 equivalent hydrogen, then 4 plus 1 is 5, we'll get quintet. Quintet means 5 peaks. The signal is split into 5 peaks. And what is the intensity ratio? Very simple. Add zeros both sides. 1 0 this side, 1 0 this side. Then sum up to two numbers. Okay, just add these two numbers. I'll get 1. These two numbers 4. 3 plus 3 6. 3 plus 1 4. 1 plus 0 1. So the intensity ratio is 1 is to 4 is to 6 is to 4 is to 1. Okay, in this way we can find the number of peaks that we get, and we can also find the intensity ratios of these peaks. Okay, take. Suppose I have if the adjacent carbon has I is equal to adjacent carbon has nucleus whose I value is 1. Then what to do? For I is equal to 1, then how many peaks we get? Number of peaks. A signal splits into peaks. Okay, how many peaks we get? Number of peaks equal to, same formula we should use, 2ni plus 1. Now in this case, I value is 1. If I put I equal to 1 here, I'll get 2n plus 1 peaks. So the signal for Ha proton is split into 2n plus 1. Okay, now listen, this is very important. Suppose I'll put n value. Okay, n value here, and I'll get peaks. How many peaks we get? Number of peaks. Then I'll put intensity ratio here. Intensity ratio. Okay. Yeah. Listen. See what I'm trying to say here. Suppose I have a carbon which has one hydrogen, and the adjacent carbon has, say for example, deuterium. Then the deuterium will split this signal. See, this is Ha proton. The Ha proton signal is split by deuterium. But for deuterium, I is equal to 1. If we have I is equal to 1 nucleus on adjacent carbon, then the number of peaks that we obtain is different actually. We should use this formula, 2n plus 1 formula. Okay, now let me give you how to do this. Listen. Suppose if n is equal to 1, if adjacent carbon has one deuterium atom, right, or any nucleus having I equal to 1, how many peaks we get? Put n is equal to 1 here. If you put n equal to 1, 2 into 1 is 2, 2 plus 1 is 3, so we get 3 peaks. Okay, 3 peaks means what is the intensity ratio? Listen carefully, the intensity ratio, the starting intensity ratio is 1 is to 1 is to 1. Okay, I have 3 peaks. Starting ratio should be 1, 1, 1. Then number 2, if n is equal to 2, what will happen? If you put n is equal to 2 here, 2 into 2, 4, 4 plus 1, 5, we get 5 peaks. Then what is the intensity ratio of those 5 peaks? Very simple. Add 2 zeros both sides. Add 2 zeros both sides. Then add 3 numbers. Add these 3 numbers. 0 plus 1 is 1. Then next 3 numbers, 0 plus 1, 2. Next 3 numbers, 1 plus 1, 3. Next 3 numbers, 2, 1, like that. So the intensity ratio is 1 is to 2 is to 3 is to 2 is to 1. Okay, I hope this thing is clear to all. Okay, now let me write one more so that you can easily understand. Suppose if n is equal to 3, put 3 here. 3 into 2, 6, 6 plus 1, 7, so you will get 7 peaks. What is the intensity ratio of those 7 peaks? Very simple. Add 2 zeros both sides. 1, 2, 1, 2. Then add 3 numbers. First 3 numbers, 0 plus 1, 1. The next 3 numbers, 0 plus 1 plus 2 is 3. Next 3 numbers, 1 plus 2 plus 3, it is 6. Next 3 numbers, 2 plus 2 plus 3, that is 7. Then we get 6, then we get 3, then we get 1. So the 7 peaks, the intensity ratio for the 7 peaks is 1 is to 3 is to 6 is to 7 is to 6 is to 3 is to 1. Okay, in this way you can find the intensity ratio of any one. See, for example, let me write one more so that we'll get some clarity. If n is equal to 4, if you put n equal to 4 here, 4 into 2 is 8, 8 plus 1 is 9, so we get 9 peaks. What is the intensity ratio of the 9 peaks? Very simple. Add 2 zeros both sides. 2 zeros. This is 2 0, this side 2 0. Then add 3 numbers. 1. Next 3 numbers. 3 1 0 4. Next 3 numbers. 6 plus 3 9. 9 plus 1 10. Next 3 numbers. Next 3 numbers. 7 plus 3 10 16. Next 3 numbers. 7 plus 6 13. 13 plus 6 19. Then again 16. 10, 4, 1 we get. This is the intensity ratio for these 9 peaks due to the splitting of the HA signal by 4 equivalent nuclei present on adjacent carbon whose I value is 1. Okay, take. So this is how splitting, the peaks we get due to splitting. And these are the intensity ratios of those splitted peaks. Okay, for I is equal to 1 nucleus. Now, we'll move on to the next one, which is I is equal to 3 by 2 nucleus. Suppose the adjacent carbon has nucleus which is having I equal to 3 by 2 value. For I is equal to 3 by 2, definitely we should use non-Pascal triangle. Non-Pascal. Right? In this case, how many peaks we get and what is the intensity ratio? Is the number of peaks or lines, number of peaks equal to, this is the general formula, 2ni plus 1. Put I is equal to 3 by 2 here. So 2 into n into 3 by 2 plus 1. This to get cancelled, I'll get 3n plus 1. This is the formula. Okay, now put n value, then number of peaks, then intensity ratio. Remember, this is also a non-Pascal triangle, okay, non-Pascal one. So let me write here. Suppose if n is equal to 1. N is equal to 1 means put n equal to 1 here, 1 into 3, 3 plus 1, 4. So we get 4 peaks. Okay, suppose I have a proton, HA, and if adjacent carbon has some atom whose I value is 3 by 2, then that atom split the HA proton signal into 4, right? And all these 4 have same intensity initially, 1, 1, 1, 1. Okay, then number 2, if suppose I have two the same nuclei having I is equal to 3 by 2 on adjacent carbon, what will happen? Number of peaks, 2 here, 3 into 2, 6, 6 plus 1, I'll get 7 peaks. What is the intensity ratio? What to do? Add 3 zeros both sides. 1, 2, 3 zeros. 1, 2, 3 zeros. Add 4 numbers. Okay. First 4 number. Okay. Yes, we'll get 1. Let it here. We'll get 1. Next 4 number. We get 2. Then next 4 number. We get 3. Next 4 number. We get 4. Next, then after that we'll get the reverse order, 3, 2, 1. Okay, so you get 7 peaks and this is the intensity ratio, 1 is to 2 is to 3 is to 4 is to 3 is to 2 is to 1. Right. Suppose if we have 3 adjacent, if we have 3 equivalent nuclei on adjacent carbon, for them, if I is equal to 3 by 2, how many peaks we get? If the n value is 3 into 3, 9, 9 plus 1, 10, we get 10 peaks. And what is the intensity ratio? What to do? Add 3 zeros. Add 3 0 this side and 3 0 this side. Then add 4 numbers. Very simple. Okay. Right? So add 4 numbers. So this will give 1. Next 4 number, we'll get 3. Next 4 number, we'll get 3 to 5, 5 plus 1, 6. Next 4 number, we get 7 plus 10. Next 4 numbers, we get 10 plus 2, 12. Then next 4 numbers, we get 6 plus 4, 10 plus 3, 13. Okay, then the reverse order. 12, 1, 2, 3, 4, 5. Sorry, 1, 3, then we get 6, then we get 4 plus 3 is 7, 10, then next 3 numbers, 3, 3, 6, 6 plus 4, 10 plus 2, 12, the next 4 numbers, 3 plus 3, 6, this is 12, I'm sorry, 12, then we get 10, 6, 3, 1. Okay, so this is the intensity ratio for those 10 peaks. Okay, take. Okay, so we'll see some examples. Right, number 1. Okay, suppose I have a compound like this, CH3, CH2, Br. See here I have taken a very simple compound. Now the question is, okay, how many signals we get, how the splitting will occur. You know, the bromine is attached to this this carbon, so these 2 hydrogens are in one environment, and these 3 hydrogen, which is far little away from bromine, okay, they are in a different environment. So this compound will give 2 signals in the NMR spectrum. Okay, signal for A proton, that is CH2 proton, and signal for CH3 protons. Now, how splitting will occur? See, in the low resolution NMR, if you take low resolution NMR, in the low resolution NMR, okay, where we plot intensity and chemical shift, right, this is TMS. Okay, we usually won't show TMS, but just for understanding purpose, I'll show. Now, listen, these 2 hydrogen, A protons, which are close to the electronegative atom. Therefore, these 2 protons, that is CH2 protons, appear or it gives signals in the low field. You know very well, from left to right, magnetic field strength increases. So CH2 protons, they are close to the electronegative atom. Therefore, these 2 protons appear in the low field. Right? So I'll get a peak, and so I'll get a signal for CH2 protons. Then I'll get a signal for the methyl. Methyl proton is somewhat away from bromine, so that will give a signal. So we get 2 signals in the proton NMR spectrum of ethyl bromide. Now, this is low resolution NMR. If you take high resolution NMR for the same compound, okay, appears like this. See, intensity and the magnetic field increases from left to right. Okay, say this is the TMS. Now what will happen? These signals get split into many number depending upon how many hydrogens are there adjacent carbon. Say for example, the A protons, okay, this is the A proton signal and this is B proton signal. The A proton signal is splitted by the methyl protons. Okay, methyl protons I value is half, per protons I value is half. Therefore, we should use n+1 rule. So the A proton signal is split into a quartet by the B protons. So A proton signal is split into quartet. Let me draw just a line. Okay, I'll get 4 lines. It will split into quartet. Okay, and the intensity ratio is 1:3:3:1. Right? And what about B proton? B protons will give one signal in low resolution NMR, and that signal is split into a triplet by CH2 proton. Here I have 2 hydrogen, so 2 + 1 is 3. Use the n+1 rule. Okay, for CH2 protons, adjacent hydrogen is 3. So n+1 is 4, we'll get a quartet. For CH3 proton, we get one signal, and that signal is splitted by CH2 protons. I have 2 hydrogen here, so 2 + 1 is 3. So the B proton signal is split into 3. The intensity ratio is 1:2:1. Okay, so this is how the NMR signal appears in the in the high resolution. Okay, so CH2 proton appears as, CH3 methyl proton appears as a triplet, and methylene proton, CH2 proton, it appears as a quartet, quartet. Okay, there. Now listen here. Suppose I will take the compound of the CH2, chlorine and chlorine. Yes, tell me how many signals we get for this compound. Yes, this compound is symmetrical, that both the protons are equivalent, so we get only one signal. Only one signal, so you will get a singlet, because they couple. The two protons will couple, no doubt, but they do not split. So no splitting. No splitting. Therefore, that one signal appears as a singlet. We say that it is singlet. Okay, it's a very simple case. Now, let me move on to the third one. CH3, CHCl, CH3. Yes. Tell me how many signals we get for this compound and how the splitting will occur. For methane proton will get one signal, and the two methyl protons will get one signal. Okay. Now which one will appear at low field and which one will appear at high field? The protons, okay, close to the more electronegative atom. See, this proton is connected to this carbon. The same carbon as chlorine atom, okay, which is more electronegative. Therefore, A proton appear in low field. Right, so let me draw here intensity. This is magnetic field strength. This is TMS. Now, yes, A proton signal, A proton only one proton. That one proton will appear in low field. In the low resolution, S will get one signal. In high resolution, that signal is splitted by the adjacent proton. See here, this is methyl. This is also methyl. They are equivalent. So 3 plus 3, I have N equal to 6 now. Therefore, N plus 1 rule, if I apply, I will get 7. So, the A signal peak, the A signal is split into 7. Septet. Yes, it's split into a septet. Okay. We know the intensity ratio. So, we get actually, if we apply N plus 1 rule, we get actually 7 peaks. Okay. 1, 2, 3, 4, then 5, 6, 7, like that. Okay, we'll get 7 peaks. Didn't draw perfectly, but we'll get 7 peaks. Okay, if I apply N plus 1 rule, right? So we'll get a septet. Septet for which hydrogen? For the A protons. This is for A protons. A proton signal is split into a septet. And what about B proton? B protons are equivalent. So these 6 hydrogen will give one signal, but that signal is splitted by the A proton. I have only one A proton. So if I apply N plus 1 rule, so 1 plus 1 it is 2. Therefore, the 6 proton signal, that is B proton signal, it is split into a doublet. Okay, it is split into a doublet with intensity ratio 1:1. Okay, right? This is for CH3 proton and this is for methane proton, CH proton. Right? Take. Now, I'm going to give you an idea to find the approximate chemical shift values of these protons. Okay? So, these are some tricks that we use, right, to predict the chemical shift values. Right? So, chemical shift values. Not just for this compound. Okay, this is applicable for any compound, right, which has some specific groups. Okay, I'll just show you. Listen. Methyl protons, observe carefully. Methyl protons, the chemical shift, usual chemical shift is 0.9 ppm. All the values are in ppm, let me write here. All the values are in ppm. Right? Whereas methylene protons, CH2 protons, right? The usual chemical shift for methylene proton is 1.3 ppm. And for methane proton, one hydrogen, and 3 other groups. We call this as methine proton. Methyl, methylene, methine. Methine protons, the chemical shift value is 1.5 ppm. Okay, so chemical shift value increases from methyl to methine. Okay, so this is first important information. Keep this in mind. Let me write one information. Now, second information. Observe carefully, very, very important. Let me take these methyl, methylene and methine groups as A. They are all A proton. Let me call them as A. Now, if this A is connected to an alcohol group, or if this A is connected to an ether group, observe carefully, very, very important. This A may be methyl, A may be methylene, A may be methine. If the A group is connected to alcohol, see OH group directly connected to this A, so this is alpha. This group is in alpha position. Okay, this is ether and this group is in alpha position. Okay, if the methyl group, methylene group or methine group present in the alpha position, meaning OH group directly attached, OR group is directly attached. If that the situation, then to the normal chemical shift, you should add a value of 2.5. Add a value of 2.5. Keep this in mind. Very, very important. Very, very important. See, for example, if methyl group is connected to an OH group, what should be the chemical shift of these protons? Very simple. Chemical shift is equal to, for methyl, usual value is 0.9. For methyl, usual value is 0.9. When it is directly connected to OH group, then we should add a 2.5. So we get the value as 3.4 roughly, 3.4 ppm. So approximate chemical shift we can predict. Right? So keep this in mind. This is rule number 2. Okay, take it. Suppose I have a CH2 group which is connected to an OH group. Can anyone tell me what's the chemical shift of this CH2 proton?
3.
Rule number 3. Okay, suppose if this A group, observe carefully, very, very important. If it is connected to oxygen atom of an ester, okay, if A group is connected to an oxygen atom of an ester, then we should add a value of 3, right, to the chemical shift value. We should add a value of 3, right? Take note. Suppose I have CH3O CO group in a molecule, right? Can anyone tell me what is the chemical shift of this methyl group? What is the usual value?
0.2, sir.
Usual value of usual value 0.9. Now the ester group, oxygen of ester group is attached. Observe carefully. Oxygen of the ester group. This is the ester group. Oxygen of the ester group is connected to this. So add 3. So we'll get the answer as 3.9. I'm sorry. 3.9. Okay, take. If CH2 group is connected, what should be the value? Can anyone tell me? What should be the value of these? What should be the chemical shift of these CH2 protons?
4.3.
For CH2, the value is 1.3 and plus 3, so you'll get 4.3 ppm. This is the chemical shift for CH2 proton attached to oxygen atom of an ester group. Okay, take. Rule number 4 is this. Listen, suppose if this A group, if it is connected to a carbonyl group, okay, alpha, right, the alpha position, suppose I have A group connected to carbonyl. This carbonyl can be a ketone, it can be an aldehyde, it can be even an ester, whatever it is. Whether it is keto carbonyl group or aldehyde carbonyl group or ester carbonyl group, whatever it is, right? This chemical shift of A, for this you should add plus 1. That's all. This is the rule. Add plus 1. Suppose I have CH3CO group. Okay. Yes, what's the chemical shift of this methyl now? Tell me. For methyl, general chemical shift value is 0.9. To this add 1. So what's the value?
1.9.
1.9. Okay, suppose I have CH2CO group, CH2CO. What should be the chemical shift?
2.3.
Yeah, 1.3 plus 1, I'll get 2.3 ppm as the answer. So, this empirical research is just an idea. Okay, it's a shortcut or trick we can say. Using this trick, we can predict, okay, not exactly, to some extent we can predict the chemical shift values of the methyl group, methylene group and methine group. Okay, take note. Suppose I have A group, this is rule number 5. A group is connected to a carbon that is connected to a carbonyl group. That is, A group is not in alpha position, now it is in beta position. If it is so, what is the chemical shift? To the chemical shift, you should add plus or minus 0.2, usually plus 0.2. Okay, we should add plus 0.2. Right? Then, if A is connected to a carbon and that is connected to an oxygen, this oxygen may be an ester, right, or maybe an ether. In that case, we should add a value of 0.6, okay, to the chemical shift of that A value, right? Now I'll go back to the compound. So the compound that I gave here is CH3, CO, CH2, CH3. It is called butanone. This compound is called butanone. Common name is ethyl methyl ketone.
Ethyl methyl.
Okay, yeah. So it has 4 signals actually. This compound will give 3 signals in the proton NMR spectrum. Okay, this is A methyl group attached to carbonyl directly, and CH2 group attached to carbonyl directly, and CH3 attached to methylene. So all these 3 protons are in different environment, we'll get 3 signals. Good. Now the question is where they will appear. We'll discuss about splitting later. First we'll find out the position. Yes? Can anyone tell me what's the chemical shift of the A proton? Why? Because for methyl group, the general value is 0.9. Now it is alpha to the, okay, methyl group is alpha to the carbonyl. Therefore, we should add a value of 1. So, the rough value is 1.9 ppm for A proton. Okay, what about B proton? Anyone? For B proton, common value is 1.3. And this is alpha to the carbonyl group, right? So, add 2.3 ppm. Very good. What about this methyl?
2.1, sir.
0.9. Okay, generally 0.9. Then
2.3.
it is beta to CO group. So we should add a value of 0.2, right? 0.2. So answer 1.1. Am I right?
1.1, sir. Yes, sir.
Okay. Now listen, let me draw low resolution NMR first. In low resolution NMR, okay, so let us say this is a TMS. Right? We see for TMS chemical shift is 0. Now chemical shift 1.1 will appear first, correct? So C protons will give a signal. This was C proton. Then 1.1, next 1.9. A proton will give another signal here, a signal here. Then 2.3 chemical shift 2.3, that is B proton will give a signal here. Okay, so this is C proton appear at 1.1 chemical shift. B protons appear at A proton appear at 1.9 chemical shift value and B protons appear at 2.3 chemical shift value. Okay. This is low resolution NMR. Low resolution. Right? If you go to high resolution, okay, these peaks get split. These peaks get split and we'll get different peaks. Okay. So how many peaks we get? So this is suppose this is TMS. How many peaks we'll get? We'll see. Now listen. First I'll take the C proton. Right? C proton. C proton is nothing but methyl group. So methyl group will give one signal. That signal is splitted by the adjacent CH2, correct? Adjacent CH2. Here I have 2 protons. So N is equal to 2. N is equal to 2. So 2 plus 1 is 3. So the C proton signal, methyl signal, the C proton signal is splitted into triplet. Is this clear to all? So the signal due to C proton is split into a triplet in the ratio 1:2:1. This is for C proton. Okay, or the methyl proton. Right? We get a triplet in the ratio 1:2:1. Then next one, A proton. A proton, listen, it is connected to a carbonyl group. Therefore, A proton signal does not split. Right? It remains as a singlet. So A proton signal remains as a singlet. It remains as a singlet. Okay. This is methyl group connected to a carbonyl. Then what about B proton? For B proton, listen, this side I have carbonyl group, but this side I have methyl group. So the methyl proton split the signal of B into a quartet. So the B proton signal is split into quartet. 1:3:3:1. Okay. So this is the CH2 methylene proton, right? Which is split into a quartet. So this is a quartet, and this is a singlet, and this is a triplet. Okay. Take note. Predict the NMR signal, okay, proton NMR signal for this compound. Yes. So this compound gives 3 signals in the proton NMR spectrum. Okay. So suppose I'll take this as A, this is B proton, and this is C proton. We'll get 3 signals. Now predict the approximate chemical shift values of these protons. Let me explain this, how we get this value. See, the chemical shift for A proton. For methyl, the general chemical shift value is 0.9. Okay, plus, and it is attached to carbonyl group. Whenever a methyl group or methylene group or methane group attached to carbonyl, we should add a +1 to the chemical shift. So the chemical shift for A proton is 1.9 ppm. Right? Then what about for chemical shift of B proton? B proton is attached to oxygen of the ester group. For B proton, the general chemical shift is 1.3. Since it is attached to oxygen of the ester group, we should add a value of 3. So if we add 3, we'll get the answer as 4.3 ppm for B proton. What is the chemical shift of C proton? Right? C proton is a methyl group. For methyl group, the general chemical shift is 0.9, and it is beta to the oxygen. This is alpha, this is beta. Since it is beta to the oxygen, add 0.6 to that. So you'll get the answer is 1.5 ppm. Okay. Therefore, in the low resolution NMR, okay, and say this is PMS. The low resolution NMR, first we'll get the 1.5 signal, 1.5 for C protons, then 1.9 for A proton, then 4.3 for B proton. We get signals like this. Okay, this is at 1.5 chemical shift, this is at 1.9, and this is at 4.3. Right? Then in the high resolution, splitting will occur. So you can draw the rough sketch of the NMR spectrum in high resolution. Okay, yeah. So I stop here. We'll discuss with more examples in the next class. Okay, and I'll introduce you what is meant by coupling constant and how the coupling constant value helpful in finding the structure of the compound from NMR data. Okay. Yeah.